So, okay, so let me repeat the question first though. So, suppose we have an Intel SGX processor that's doing some computation in an enclave for a client, right? The client wants to communicate sensitive information to the SGX enclave. So, there must be some secret channel that needs to be set up between those two entities, right? So that's important. So, the first thing that you could do is, you could, as a client, send your public key to me. Let's assume you have registered before, so a correct enclave would have been able to verify, okay, you belong to, this belongs to Ha, and so on, you're in my database, and I will give you the service that you asked for because you paid for it, something like that. Okay, so your public key comes to me, and now the enclave is going to say, I like to have your sensitive information. Here is a key that you can use. So it produces a key, but you can say, in this particular implementation, I don't know whether there may be other solutions, but that key needs to be encoded in a report. And that report is going to be sent to you. The idea is that I'm going to sign that report with an attestation key, that is the ID, that you can verify as belonging to this SGX machine. And not only that, the report also includes a measurement of the enclave. So I also know that the key was computed by an enclave with that particular measurement, right, at this particular processor. So now when I check the measurement, and if this would be a malicious enclave, then it's not the same identity as what I would expect. So I know the author of the original enclave. I do not need to know the code of the enclave, but if I trust the SIG struct of the author, that the author created the right signature on that enclave that it authored, which includes the identity and all of that stuff, then I'll take that and I match the identities. You do that, right? You match the identities, and now you know for sure, you verify that you're talking to a trusted person. Now the key that is transmitted in the report is obviously encrypted by your public key, so that the man in the middle cannot see it. So now you decrypt according to your private key, you get a key, and now you have a secret channel with a joint symmetric key. That's one way to possibly set that up. Should I write it out on the whiteboard?
So you mean that there's no chance to have that kind of attack?
Yeah. So you know what?
But you know the point here is I already verified the identity of the enclave.
Yeah. So it's like
before I give the secret key to him.
Yeah. So we have an enclave, and there is a measurement that is taken from this. Then there is an author who does this, and you create a SIG struct, which is effectively a signature, right? And I trust the author. There's a verification key for that author, right? So I can verify that. So here we have a client, and the client says, okay, I want to start communication with you, right? So here we have effectively the enclave, which is at some, Intel SGX processor, and the client sends, for example, a public key over. Why not? So that's the method that I just described. And this enclave has a few instructions, and one of the instructions is that it says, I recognize the public key, and yes, service is paid for. Okay, that's great. Then the next step would be something like, Okay, let's create a report. And in the report, I will have the encryption of maybe another public key of some symmetric key, for example. And as you will see on the next slide, part of the report would also then later on be the measurement. And actually, if you do all this, you want to be fresh. So let's add a nonce and add a nonce in here. And this is being transmitted over through remote attestation that we are going to explain on the next couple of slides. And effectively what it is that there will be a certificate over here, will be a signature that uses an attestation key. So what's the client doing? It takes from Intel's professional key provider service, I think that's what it is. It will take a verification key and you verify the signature, right? So that's good. So what does that tell me? It tells me at least that this was constructed at that particular Intel SGX processor. So check. So you check on the identity of the CPU, if you will. Next, you also check that it must have been created by a secure enclave, because the attestation key, why is that? Because the attestation key is only accessible by the quoting enclave or the SGX hardware. So we'll come to that in a moment. A caller enclave, right, can actually it's not so I made a tiny bit of a mistake. In this particular case, the attestation key is just known by the quoting enclave. So, in the quoting enclave, you trust because effectively the signature processing is a little bit more complex. The identity of the quoting enclave is obviously embedded in that, and that is what the hardware is doing. So you trust that it comes from the processor, so you know that that is all happening properly, and you know that this is trusted. Okay, fine. You trust Intel to have done a good job, and that software is not vulnerable to some kind of software vulnerability. So now you have verified the signature, and what you also know is that you can now also verify the measurement, right? How? Well, I have the SIG struct, right? That I can verify with the author's verification key, and then so this is getting a little bit messy, but the point is that you verify that over here with this measurement, right? Effectively, you verify that, and in order to make that happen, you of course need the verification key of the author. Okay. So now, you trust the author, that's the one you're dealing with, obviously. So you now know that this particular enclave is actually executing. So now you know that K is generated by the correct enclave and not a malicious enclave, right? And that's how you bootstrap trust. So now, of course, you decrypt it, right? The report is now, okay, there it is. So man in the middle can only see an encryption under your public key, so that doesn't help. So that's one way to approach it. It depends a bit on your application, I suppose, whether you have public keys of clients or not, but that's one approach. You could even have secretly shared a secret key, maybe a priori or things like that. But that's how you could potentially transfer or create now an enclave client secure channel. That's one approach. I'm not sure whether it's the best approach, but this at least shows a lot of elements. Cool. All right, let's continue with these slides though, because what I really wanted to say is that isolation really talks about the secure enclave itself. It's not leaking anything. So it's a hardware environment, if you will, like an actual computational environment that is not leaking any information. Beautiful. The application code that runs in it can still be buggy, and you can exploit it maybe, and so forth. That's not what we're talking about here. Now, when application code is actually executing in such an enclave, then I want to make sure that I can verify that whatever comes out of there is authentic and fresh. So, so why software attestation, right? So, effectively, an enclave author creates an application module which should be executed in a secure way, since it deals with sensitive information, right? So, first, application modules should be verified. So that's what I just wanted to say, using, for example, proof carrying code, etc. So that is outside of our adversarial models that we discuss in secure process architectures, right? That's the designer's thing. Second, even if the application module is formally verified, the module should be executed in a secure environment which is trusted to resist strong adversaries. So we want to inherit the security posture as promised by Intel SGX, our enclaves. Okay, that's what we would like. So now during the application module's computation, the enclave wants to report output to some remote party. Now how can the remote party trust the reported results? Now we just discussed a little bit about that, but how do we generate that signature in the first place? Okay, so let's talk about that now, because it's a little bit more complex. So the main idea is to challenge the enclave first with the random nonce. I did it on the whiteboard also, which the enclave includes in its report. Because if you now check the nonce, right, in our example, you know it's fresh. So that's important. Now the SGX hardware is going to sign a report with an attestation key. That's what we just talked about. The remote party now verifies the signature with a public verification key. Fine. And this public key comes from some trusted database, which is that Intel Professional Key service and so forth. And the signature should convince now the remote party that the enclave's code was executed in a secure enclave with its resistance to certain attacks, as we have discussed in the previous many lectures. So now the report can as such be trusted to come from that enclave. So how do we do that though? So notice that the signature that we just talked about is created by a quoting enclave. It's not created by the actual enclave. So there's lots more machinery at the back to it. That we need to understand that trust really implies trust in the next level and so forth. So you bootstrap trust along the way. Now, here's the little remark about a nonce, right? That's used for freshness. So what does this signature attest to exactly, you know? What does it imply? So what is this report signature? So a straightforward solution would be, when an enclave is executing, it calls e-report. I want to report something, fine. The SGX hardware, like the microcode that implements the e-report in this particular case, takes over, and a simple solution will be, it simply signs the report, right? Why not? The enclave's measurement is also part of the signature, and the nonce, obviously. That will be a very straightforward solution. And it uses a secret key with corresponding public key certified by Intel stored in its database. We call that the attestation key. Wow, that's very simple. This unfortunately does not work in practice. because the signature scheme is too complex. When we talked on Monday, the signature scheme that Intel proposes is one that also has a few nice properties. You can renew attestation keys, and then you have unlinkability and some anonymity, so there are some really nice other features that Intel has included, but the signature scheme is simply too complex. You don't write dedicated hardware for this. So you want to do it in software. Now the software part needs to be executed in a secure environment to begin with. What do? Let's create a special signing, or what we call a quoting enclave, authored by Intel and executed in an SGX enclave. That's cool. Okay, that's a nice hardware-software co-design. But now I need to solve a problem. And the problem is that now the application enclave needs to communicate its report to the quoting enclave to begin with. So we need to verify this. The quoting enclave needs to verify its authenticity, right? So that it can sign for that application enclave. So it needs to be sure that there's no one malicious at the other end of the communication line. So we need local attestation within the processor. So this is actually a general feature. So any caller enclave can communicate a report over an authentic channel to a target enclave. Now the remote party now should verify that the trusted quoting enclave software, that the trust, right, that it's done properly, has produced the signature. And this is remote attestation. So now let's have a look about the attestation key, right? Intel SGX does not fuse one static attestation key. So far we could just have worked with one key, right? But why does Intel not do this? Well, once you have multiple attestation keys that can be associated to the processor. Why? The processor may change ownership. I can sell it. That's a very important property for a product. But it also means I don't want to leak any privacy, right? I don't want to link, say I buy this from you, Hamza, and I do not want to have any linkage. There should be some unlinkability property, or nobody should be able to find it out from our ciphertexts or signatures in this case, right? So that's what this special signature scheme does for us, but we need multiple attestation keys. Oh damn, how do we do that? We need a dynamic solution. That's why Intel SGX fuses a provision key, which is a master key stored by Intel. And the provision key is used by this provisioning enclave in the SGX processor, who communicates with Intel to create an attestation key. And again, this can be done in some unlinkable way, apparently. So I've not figured that out in its most detail. But this is another example of a software-hardware co-design where we use a provisioning enclave now to make that happen. Yeah, go for it.
Yep. So this Intel SGX, they can be different processors, right?
Mm-hmm.
So each processor has a different provision key, or
Yep.
all of them have the same?
Each Intel SGX processor has its own unique provision key. Absolutely.
For the provision key,
Hmm?
where the provision key can be.
So the provision key is kept in two spots. One is it's fused in the SGX processor, and it's also stored in a database at Intel. It's stored at two spots. So why is that? Because now the trusted authority, Intel, can effectively say that this particular verification key that belongs to that attestation signature key, belongs to that particular. I've issued it. So now you can verify that, and you trust that you need to get your public key for signature verification from somewhere, from some trusted authority. Remember our discussion on the crypto basics? There is some trust at the bottom somewhere. We need a trusted third party here, which is now this. So this is really all about key management, by the way. Did you see how complex key management can become, by the way? Anyway, so the attestation key also needs to be stored somewhere in the processor, right? It's not fused in. Instead, Intel SGX fuses a sealing key, which is not known to anyone but the processor itself. It's created at random by the processor itself and not communicated to outside the processor at all. So it uses that sealing key to encrypt, to use authenticated encryption of the attestation key so that the quoting enclave can get it and no one else. So now you're in good shape. You now can trust the signature to be produced by the quoting enclave, because the identity of the quoting enclave is of course embedded and so forth. And you know that that attestation key could only have been accessible by the quoting enclave through the use of the sealing key, that quoting enclave is allowed that the quoting enclave can use, because the sealing key is actually used to create another authenticated encryption key that mixes the sealing key with the quoting enclave's identity actually. So that's sort of how it works. So we don't go into detail here. There's other details in the other slides that we discussed on Monday though, but that's effectively how it works. So now we trust that. So that's pretty cool. So let's think some more about bootstrapping trust. So we trust that the sealing key is only known by the SGX hardware, right? And the provisioning key is only known by both the SGX hardware and Intel's provisioning service. These keys bootstrap trust in the generation of an attestation key with Intel's provisioning service. So we had some diagram at one of the future slides, one of the ones that we discussed on Monday, that shows that relationship. But anyway, conceptually, this is effectively what happens. And now you also have secure storage of the attestation key by the Intel SGX processor that uses that sealing key, right, that we just discussed about, mixed up with the identity of the quoting enclave so that it can be found out by the quoting enclave. So the application module in a caller enclave, right, generates a report with the client nonce and asks the SGX hardware to MAC the report with a MAC key, because now we need to talk about remote local attestation. And this MAC key is derived from the target enclave's report key. What is that? And the caller enclave's identity. Now, the target enclave's report key is something that is uniquely computed from the sealing key of the processor together with the target enclave's identity. So it is possible for the target enclave to call this getKey, eGetKey functionality. And eGetKey functionality can be called by any enclave, but when you call it, the hardware is simply using the sealing key and mixes it up with your identity to give you a MAC key. So that MAC key is unique to each, report key. So that report key is unique to each enclave. And in this case, the target enclave can reconstruct its own report key and then can verify, because now it can compute the MAC key by joining the report key with the caller enclave's identity. And now it can check the MAC. So that can all be done in software. And the SGX hardware, right, is being used by the caller enclave who does not know the report key of the target enclave,